Now, the NMR has more information to give us than just number of chemically inequivalent hydrogens. For example, the relative intensity of the proton signal also provides information about the compound structure. So the area under the NMR signal here is proportional to the number of absorbing protons. And an NMR spectrometer can integrate the area under the curve and print out a stepped curve shown here, or an integral on the spectrum. Now, the height of each step is proportional to the area under the peak. And that, in turn, right, is proportional to the number of absorbing protons. So, modern NMR spectrometers will automatically calculate and plot the value of each integral in arbitrary units, right? So like here we can see there's a 1 and a 3 kind of hidden up there. The ratio of integrals to one another gives us the ratio of absorbing protons in the spectrum. So, for example, if we were looking at this molecule, we would say, look, there's a 1-to-3 ratio there. Now, it's a ratio, not the absolute number. So notice we've got 3 protons here and 9 protons. 3 times 3 is 9 protons here, and that reduces to a 1-to-3. Let me kind of dig around in that for a minute. And so what this means is, with our integrals, if we had these 2 molecules, right, they both have 2 distinct sets of protons. So this would give 1 peak, and then these would give 1 peak. And then these 2 are in the same chemical environment, so they would give 1 peak, and this would give 1 peak. The ratio of protons here is 3-to-1, and then the ratio of protons here is 6-to-2. And though that also reduces down to 3-to-1, which would give the same ratio as what we see up here, right? Which is 3-to-9, right? Or 3-to-1. So you have to be careful. You have to remember that that's the ratio, not the absolute number, okay, of absorbing protons. Now, NMR spectra also has peak splitting, which gives us just a wealth of information. So let's talk about that for just a moment. So, when we look at this molecule shown here, okay, what we find is that these protons, one of them will give us 2 signals and the other will give us 3 signals. Now, everything that we've looked up to this point has been really limited to single absorptions called singlets. Now, often peaks for different protons are split into more than 1 peak, and this is called spin-spin splitting. Okay? Now, when we talk about this, spin-spin splitting only occurs between non-equivalent protons on the same carbon or adjacent carbons. So when we look at this, right, if you have 2 peaks, it's called a doublet. And if you have 3 peaks, it's called a triplet. And then here's the number of peaks and their names that they're referred to. Over 7 is generally referred to as a multiplet, but this is kind of a fuzzy line. I've seen some people refer to things like septets or sextets as multiplets as well. So just kind of be aware of that. So maybe the burning question in your heart is, well, how do things like these doublets occur, right? So when we talk about this being a doublet and this being a triplet, right? What's happening here is, and let's go to the next slide because I think that will help us. What's happening is that when this molecule is placed in an applied electric field, right, the adjacent proton of the CHBr2 can be aligned, right, with or against the magnetic field. So let's look at that a little more specifically. So we have a Br CH2 CHBr2, okay? These protons right here show up as a doublet. This proton right here shows up as a triplet. The way we know this is called the N+1 rule, where we look at the carbon, the hydrogens on the carbon next to this, and it's 2 + 1, which gives us 3. For this doublet, we look over here, we see there's 1 there, and that's 1 + 1, and that gives us 2. So that's how we can look at the structure and figure it out, but the question, of course, is why this is happening. So we are focused on this doublet with the CH2 right here, okay? So we have those 2 protons, and they're placed in the electric field. So they can be aligned with or against the external field, okay? So those absorbing CH2 protons feel 2 slightly different magnetic fields, okay? One that's slightly larger than the applied magnetic field and one that's slightly smaller than the applied magnetic field. So they absorb at 2 different frequencies, and so they split a single absorption into a doublet. So here's the deal. If you have a proton with no adjacent protons, that absorbing proton only feels 1 magnetic field. If you have a proton or set of protons like we do with 1 adjacent hydrogen right here, okay, it's going to feel 2 different fields, and so they absorb at 2 different frequencies, and that's why we end up with a doublet. So 1 adjacent proton splits an NMR signal into a doublet. Now, another thing that we get is we can measure the distance between these 2 peaks. When we measure this, that frequency difference, so I'm going to come here and I'm going to say we're going to measure this. That frequency difference is called the coupling constant. It's represented with a J, okay, and it's measured in hertz. Between 2 peaks of, in this case, 2 peaks of a doublet. Now, let's talk about how triplets arise. So we saw a triplet before. Let's talk about how that happens. So now we are looking at the same molecule, and we are interested to see how we get a triplet for this proton. Okay, so that we're going to call our absorbing proton, and it gives us a triplet. So when it's placed in a magnetic field, the adjacent protons here, which are labeled A and B, can be aligned with, both aligned with, right? One aligned with and one against, both aligned against, right? Here. And when that happens, this absorbing proton feels 3 slightly different magnetic fields. One slightly larger than the magnetic field, one slightly smaller than the magnetic field, and one the same strength as the magnetic field. And so because the absorbing proton feels 3 different magnetic fields, it absorbs at 3 frequencies in the NMR spectrum, and it splits a single absorption into 3 peaks, and this is a triplet, okay? And so that's how we get a triplet. Now, maybe the burning question in your heart is, okay, that's great. Why is this one bigger than these two? Well, there are 2 different ways to align one proton with B naught and one proton against that B naught. Okay, so it's this right here that we're talking about, and that corresponds to the middle peak here. Okay, so because there's those 2 ways, the middle peak here is twice as intense as the 2 outer peaks, and that makes the ratio 1 to 2 to 1 because there's 2 ways that that proton can align with or against the field, right? Now, when 2 protons split each other, they are said to be coupled. And the really nice thing about that coupling constant is it's equal for coupled protons. So the coupling value So this means that you can figure out, if you make these measurements in between your peaks and figure out these coupling constants, you can figure out which protons are adjacent to each other, right? And so you can figure out what protons are splitting each other. And that is so helpful with really large, complex molecules. Now, we have 3 general rules that describe the splitting patterns that we commonly see in proton spectra, okay? And so I have these out here for you. Basically, equivalent protons do not split each other's signals, okay? So if we look here, what we're saying is, look, if HA and HB are equivalent, they are not going to split each other's signals, okay? If these are non-equivalent, right, then they will split the signals, okay? And then a set of n non-equivalent protons splits the signal of a nearby proton into n+1 peaks. And I've already talked to you about this before. This is the n+1 rule, okay? So the splitting patterns that we see really come down to, are these protons equivalent or are they non-equivalent? Are they in the same chemical environment or are they in different chemical environments? Now, one other kind of caveat that I want to add is that, right, splitting is generally not observed between protons that are separated by more than 3 sigma bonds, right? So if we look here, HA and HB are separated by 4 sigma bonds, 1, 2, 3, 4, and so they're not going to be split, okay? Another example here, these two are split by 4, they're not going to be split. So really, more than 3 sigma bonds, we're not going to see any splitting. So let's look at some common splitting patterns that we observe in a proton NMR. So here are some common patterns. Now, a big thing for you to remember here is this is for non-equivalent protons. So, for example, right, we have a proton here and a proton here. They're in 2 different chemical environments for some reason. They are non-equivalent, okay? So, when we look at this, we can see the splitting pattern here, right, is that we get doublets in both of these cases. And so, if, for example, you have a proton here next to a 2 protons, you would end up with a triplet. And then this peak would give you a doublet, okay? These would be 2 triplets. This would be a quartet, shown here, and that would be a triplet, shown there. So this is very helpful, and it helps you identify, along with the chemical shifts, what, where your protons are and the environment they're around when you have an unknown. So I want to do another example. I want us to look at this guy. And I want us to figure out the splitting for these protons, and these protons. And so if you want to stop and try this on your own, I highly suggest that, and then just kind of restart the screencast. But when we look at this one, and we're going to use this N+1 rule, we say, okay, what other protons are around these protons that could split them? Well, they're at the end of the molecule, so there's nothing on this side, and there's an oxygen here, and that has no protons, so that's going to be 0 + 1, and so that should just be 1, and so that would give us a singlet. So when we look at the spectra, we would expect there to be a singlet for that CH3. Then we are going to come here and look at the CH2. And when we do this, we look to this side and we say, okay, there's no protons there. But we look here and we say, hey, look, there are 3 protons here. And so we can say, great, according to the N+1 rule, that's 3 + 1, that gives us a quartet. Okay. Then we can look at these 3 protons here, and we can say, all right, I wonder what type of peak they would give us. So there's nothing over here. We look over here, there's 2. N+1, 2 + 1, that gives us a triplet. So we can use the information about splitting as well as the shifts and identify the peaks and then identify the structure of the compound that we're interested in. Now, up until now, we've really looked at examples where the absorbing proton has only 1 or no adjacent carbons, right? So there's not adjacent carbons on both sides. So I'm sure the burning question in your heart then is, what do we do when we have protons on both sides of a carbon instead of just 1? And the answer to that sort of it depends on what type of carbons those are, and protons. So the first thing we're going to look at are ones that are equivalent. So when we come over here, this is an example where we have equivalent protons. So we're sitting here and we're with equivalent protons. And what do I mean by that? Well, if we look at this molecule here, we've got one proton here, and then we've got protons on adjacent carbons that are equivalent. So these two guys are equivalent. We're going to see that we would predict only 2 peaks, right? And so now we need to predict the splitting. When you have 2 or 3 sets of adjacent protons that are equivalent, use the n+1 rule to determine the splitting. Okay, so we would come here and we would say, all right, let's figure out the splitting for HB. Okay, we've got 3 protons here, 3 protons here, n+1, 6 + 1, that gives us 7. We would expect that to be a septet. 1, 2, 3, 4, 5, 6, 7. It's right there. Okay, and then of course we would just determine HB like normal. Sorry, HA like normal here, where we would say, okay, look, these two are going to give us 1 peak. There's 1 adjacent proton to split them, and so we would expect that to be a doublet, which is going to be right here. Okay. Now, what happens if they're not equivalent? And the answer to that really depends on if they're in a flexible alkyl chain or if they're involved in a ring or double bond. And so we're going to look at a flexible alkyl chain first. So in a flexible alkyl chain, right, the N protons, which remember that's from our n+1, right? So whatever number of protons that is, let's say N alkyl protons, on 1 adjacent carbon. And now we're going to introduce another variable, the M protons on the other adjacent carbon split the signal into M plus N plus 1. And so what does that mean, right? Well, when we look at this, we have 2 carbons here and 3 carbons here. So we're looking at the splitting for HB, okay? When we do this, even though these are in different chemical environments, they are so close, they're going to split the same way as if they were chemically equivalent, right? So what we would do then is say, okay, N plus M plus 1. So 2 plus 3 plus 1, we would expect that to be a sextet with 6 peaks, and it is, right? And so with long chains, this is what we see. It follows that same pattern. Now, let's look at an example where the absorbing proton is flanked by 2 sets of adjacent protons, where one of those is bonded to a ring or a double bond. And this is where we're going to see something different. So when we look here, right, what you have is this guy here, this HA, okay, and the HB here, and then the HCs here. Okay, so we've got 3 protons. This is the only one where there are protons on 2 sides. So that's what we're really going to focus on and talk about, is this guy right here. Okay, so when we look at those splittings and it's around a double bond, right, the signal for him or ring is going to be n plus 1 times m plus 1. So what happens here is that we have that HB, okay, and 1 HA is going to split that into 2 peaks, okay? So he gets split once, and then he's going to get split again by these HCs over here. And so those peaks get split into 3 peaks here and here. And so you end up with something called a doublet of triplets, because this guy split first into a doublet, and then these n plus 1 split into triplets here, right? And so you get a total here of 6 peaks. So the way that we can calculate this kind of quickly is to say, all right, 1 plus 1, which is from that HA, and then 2 plus 1, which is from the HC, and so that's 2 times 3, which gives us 6, which is what we observe here, okay? So if this is across a double bond or with a ring, then this is the formula that we use, okay? I want to do another example, just for funsies. Let's say we have this guy. And I'm going to call, okay, and let's call these HA, okay, just so we know what I'm referring to. So this is A, B, and C. And let's say we want to figure out the splitting for B here, which is in between these, okay? And so to figure out the splitting for B, we would say, okay, that's attached to a double bond. So we're going to do N plus 1 and M plus 1. So I would look at what's next to it. So over here we've got 3. So that would be 3 plus 1. And then over here we just have 1. And so that would be 1 plus 1. So that'd be 4 times 2, and that would be 8. And so we would expect HB to give us a peak of 8. We'll continue to do examples in class, and as always, if you have any questions, please feel free to stop by my office.